This resembles a crowded alien forest, but it is actually a simulation of the human colon, a dense, competitive ecosystem of trillions of dynamic microorganisms. To keep this ecosystem running, it requires highly specific fuel. While simple carbohydrates from our diet are rapidly absorbed early in the small intestine, specialized complex carbohydrates possess chemical bonds that resist gastric acid, arriving completely intact at this lower environment. We call these intact resources prebiotics. They are non-digestible dietary fibers that safely bypass human digestion to serve as targeted nutritional substrates exclusively for beneficial colon bacteria. Clinical research identifies 3 primary classes of these indigestible resources: fructooligosaccharides, galactooligosaccharides, and inulin. Without these specific fibers surviving the digestive journey, the colon's ecosystem lacks its foundational energy source, leaving the beneficial species unable to generate the energy required to survive. To reinforce this environment, we often introduce probiotics, live health-promoting bacteria ingested to improve microbial balance. But these isolated probiotics face an immediate biological challenge. They are vulnerable new arrivals, being dropped into a fiercely competitive, fully established territory. In this population simulation, we see the consequence of arriving without food. Because the new bacteria lack immediate access to their preferred nutrient sources, they are rapidly outcompeted and eliminated by the trillions of resident microbes already adapted to this environment. This lack of a sustained energy source explains why introducing beneficial life into a host ecosystem is rarely successful unless the specific nutritional infrastructure required to sustain that life is introduced alongside it. The scientific solution to this starvation is straightforward: pairing the live beneficial species directly with their required fiber substrates. This integrated delivery system is called a synbiotic. As seen here, the active bacteria travels firmly attached to a complex fiber structure. The microbial settler arrives with its own packed lunch. This built-in survival ration allows the introduced bacteria to immediately generate energy and multiply, giving them the resources needed to adhere firmly to the intestinal mucosal lining. Once established, these bacteria initiate a process known as competitive exclusion. By consuming local resources and physically occupying space on the gut lining, they metabolically starve out invading pathogens. By providing this specific fuel, the host ensures that beneficial species have the distinct metabolic advantage required to claim territory and stabilize the intestinal landscape. Once the beneficial bacteria have their fuel, they begin dismantling the complex chemical bonds of the prebiotic fibers, a task human enzymes cannot perform. This metabolic breakdown process is known as fermentation. This mechanical process produces short-chain fatty acids, or SCFAs, which regenerate the colon. Among these outputs, butyrate is uniquely critical. Notice it's separating from the stream. It serves as the primary energy source for the intestinal wall. Bacterial fermentation effectively functions as an internal manufacturing plant, converting indigestible matter into the life-sustaining chemical outputs the host requires. This butyrate travels directly to the physical walls of the colon to be consumed by the host's own tissue. The inner lining of the colon is made of specialized cells called colonocytes. As seen here, these cells rely heavily on microbial byproducts for their energy, absorbing them to maintain the integrity of the barrier. Energized by this fuel, the colonocytes produce tight junction proteins. These act as biological mortar, sealing the microscopic gaps between intestinal cells to prevent the barrier from leaking. These outputs also trigger the release of glucagon-like peptide 2, a hormone that accelerates tissue healing and suppresses systemic inflammatory triggers. This shows that the human intestinal wall is not a static barrier, but an active structure entirely dependent on bacterial outputs to remain secure. If prebiotics are consistently absent from the diet, this protective chain reaction reverses. Without fiber, beneficial microbes starve, leading to a state called dysbiosis. Inflammatory bacterial species then seize the available biological real estate and multiply across the intestinal wall. The production of tight junction proteins halts. The intestinal barrier weakens, opening microscopic gaps. Toxic lipopolysaccharides slip through these gaps into the bloodstream. This triggers a state of chronic alarm known as metabolic endotoxemia, visible here as a spike in systemic inflammation markers. Skipping the prebiotic-packed lunch starves the body's primary border patrol, allowing localized microscopic failures to become body-wide systemic threats. Restoring balance requires the consistent synchronization of high-quality prebiotics with multi-strain probiotics. This creates a state of eubiosis, an optimal, self-sustaining balance where beneficial bacteria dominate and regulate the biological environment. This balanced state leads to measurable improvements across the body. Detailed clinical analyses show that eubiosis is associated with improved insulin sensitivity, lower body mass index, and a measurable reduction in systemic inflammatory markers. These benefits extend to cardiovascular health, where researchers observe significant decreases in total blood triglycerides and low-density lipoprotein, or LDL, cholesterol. Long-term health is determined by more than just what the host digests. It depends on effectively feeding and defending the invisible ecosystem that governs the body's primary borders.